So we're going to start off with logs. We're going to start off with the bookwork shows you right here. We're talking about a log with base b. Log base b of y equals x. If and only if b to the x equals y. This is what I call the definition of a log. It is the most important thing that we learn in this class. Log base b of y equals x. If and only if b to the x equals y. That is what I mean when I say the definition of a log. It's not what a log is. It's the definition of a log. It allows you to go from logarithmic form here on the left to exponential form. 95% of your questions in the next 3 or 4 days of class can be answered by using the definition of a log. You will hear me say, press the button, use the definition of a log. I want one like this. But I wanted to say, use the definition of a log. And so I had some students made one. We got this one. And we've got this one. But nothing as good as, I want that kind of sound from a button. You can make that happen? You let me know, we'll get you some extra credit. But nobody else has been able to do that yet. Again, the definition of a log right here. In my house, we used to have it, it's probably still somewhere in a cupboard. We have a yellow bucket from when the kids were little. And in the bucket is a bunch of plastic blocks of different shapes. On the top is a white cover, and on that cover are holes. Square, round, circle, or star, moon. And you dump all the blocks out, put the cover on, and the kid sits there trying to put the blocks in the holes. And they figure out that the shape has to match the hole. That's what this is all about. The letter B right here goes here, B. The Y goes right here. And the X goes right here. You'll hear me talk about making the loop. This B raised to this power is equal to Y. That's what this is telling you. B to the power of X is Y. B to the power of X is Y. Logarithmic form on the left, exponential form on the right. Some minor stipulations. B has to be a positive number. Y has to be a positive number. And B cannot be equal to 1. Some of those will make more sense later in this period. It'll make more sense why you can't have Y be a negative or B be a negative. Logarithmic form on the left, exponential form on the right. It's read log base B of Y is equal to X. That's what this says on the left-hand side. Not being able to say that correctly is not where you need to be right now. You want to be able to talk the talk. Log base B of Y is equal to X. Hey, Rose, you had a question? For what? The first slide said the same thing that's right here. Okay? What's a log? That's the big question. What is a log? Multiple choice. Something you do when you turn on your computer. That's A. Something you throw in a fire. That's B. It could be an acronym. Stands for Lost Old Goat. Could be. You could come up with something better, but that's what I got right now. It could be an exponent. And it could be the thing that I had the most difficulty with when I took this class. Or it could be everything that I just mentioned. Sure, it could be all of the above. But a log, I couldn't do logs to save my life when I was in Algebra 2. Part of it was, I had that sleeping thing. So I think I just totally missed out on it. So when the log questions were on the test, I just skipped them.
Were they easy?
No, I couldn't do them. It was one of those things I just couldn't do, and I struggled with logs. And then I was in a class, and they explained logs, and it was like someone flipped the light switch. And I went, really? I had all this trouble for all this time, and that's all a log is, an exponent? It's that simple, and it behaves just like all the properties of exponents that we learned already? That's it, and that was it. Logs are exponents. A log is a power. So when I ask you the log of 100,
10.
I don't expect you to know. But I do expect you to take out your calculator right now and make sure that you can find the log button and find out that the log of 100 is really 2. And the log of 1,000 is really 3. And the log of 10, what's the log of 10? 1. And if you do log of 85, 929. And just for fun, the log of 0.1, -1. Now remember, a log is an exponent. Look at this. The log of 0.1 is -1. The log of 10, the log of 10 is 1. The log of 1,000 is 3. The log of 100 is 2. And the log of 85, which is between 10 and 1,000, or 10 and 100, is between 1 and 2. Exactly what we would expect.
So is a log just finding the exponent for something with base 10?
No, for this one it is. Bear with me, I got a whole lesson today. All right, a log is an exponent. All right, log is an exponent. Two basic logs that we want to start with. One is called the common log. One is called the common log. The common log is when we talk about base 10. But remember, b can be anything. But if it is 10, we call that the common log. In log base 10, we simply write log. We do not write the base 10. It's like a square root. You don't put the 2 in the index. Log base 10, we're just going to call it log. So when we do log of 100, like we just did a moment ago, log of 100, there's no base 10 written here. You get a 2. The log of 100, the base 10 is understood. And you're asking 10 to some power would equal 100. That power is 2. So the log of 100 is 2. Remember, a log is the power. It's what power do I raise base 10? What do I raise 10 to get to 100? What do I raise 10 to get 100? That's going to be 2. So the log of 100, again, is 2. The log is just a power. The log is a power, and that's it. If the log is base 10, we call it common log, and on your calculator is the common log. LOG means common log on a calculator. The second base that we like to work with is base E. What is E? What's E? Huh? It's more than just a variable. It's Euler's number, which is the limit of 1 plus 1 over n to the n power. And it's 2.7 and change, right? Kind of discovered that yesterday. Euler's number, if log base e, we call that the natural log. Or as my research shows, in Europe or in France, they call it the log natural. And the abbreviation that was given to log base e is ln, log natural. So when you do something with log base e, or natural log of 7, when you do this on your calculator, you're saying e to some unknown power is equal to 7. E to some unknown power is equal to 7. And we don't want to have to do guess and check. You have an ln button on your calculator. So you should look for that button right now and see that the natural log of 7 should be 1.9946. Okay, it's less than 2, it's more than 1. Is there anyone who's not able to find the natural log button? Do you remember where e to the x was yesterday?
Yeah.
Right next to e to the x in that menu is the natural log button.
Wait.
It says lnx.
Wait, because I was supposed to check log, right? So. Are you just going to say LS? Okay, I got it.
Wow. Got the right on the head there? Okay. Wait a minute. No, wait. Got it. No, got it. Wait it. No, got it. No, wait. You sure you have it? Okay. So natural log of 7 should give you 1.946. Okay. Now some of you have the calculator that looks like this. It says log and there's a little box. And then next to it is another little box. That's the magic button. That calculator lets you do any base. Okay? If you have log and you have these, this is one button, you can put in anything you want for the base and anything you want to take the log of. The base can be anything. The rest of us mere mortals, we can work with logs in general. So on your calculator, we have base 10 and we have base e. Those are the ones we want to work with. So when you look at this from, this isn't no calculator stuff. This is, do you understand the definition of a log? The definition of a log says, bless you, make the loop. We're in logarithmic form. 2 to the power of 5 is equal to 32. 2 to the power of 5 is equal to 32. We're switching log form to exponential form. You want to be able to go back and forth as easy as can be. Log base 2 of 32 equals 5, 2 to the 5th equals 32. Try B, C, and D on your own. Spence, what's this one going to look like? 10 to the 0? 1, perfect. Christo, how about the next one? Yeah, but give it to me exponentially. Is equal to 9. So again, we're making this loop right here. Hannah, what about the last one?
1/5 to the -2 power is 25.
25. And again, I'm not saying that this is a correct statement, which it is a correct statement. I'm just saying exponentially, that's what it's going to look like. That's what it's going to look like. And again, we're not doing this to, wow, look at what we did. Mom, come see my work. This is not impressive. This just means you're understanding the definition of a log. If we go this way, now we're in exponential. Can you go back to logarithmic?
Yes.
Do it. So switch these to logarithmic form. And again, we're just going backwards on the definition of a log. Nina, how about the first one?
Log base 2
Of
of 8.
8. Fantastic. Log base 2 of 8. We're not multiplying. It's log base 2 of 8 is equal to 3. Samana, how about B?
Log base 3 of 81 equals 4.
Perfect. Log base 3 of 81 is equal to 4. This is the key. In the next 3 days, when you come, Ms. Walker, can you help me with this problem? 9 out of 10 times or more, it's the definition of a log that you need to apply. Press the button. Just, bam, use the definition of a log. Over and over and over again. I don't know what to do with this problem. Use the definition of a log. This is just a restatement of what we already said about common and natural logs. Base 10, base E. This is the book word. All right? When we're natural log, it's e to the power equals y. And we use natural log for this stuff. Base 10, we use common log. These two you're going to evaluate with a calculator. This is boom, boom, boom. 5 seconds on each one. You don't want to waste time on this. This is a straight calculator deal. You're just getting comfortable using your calculator. You should have some sense, at least with common logs. 0.85. You got to realize, where is 0.85 going to come? What power do I need to raise 10 to get to a 0.85? Hopefully you have a sense of that. What is the log of 0.85? Press on the button.
Negative
Negative
0.07.
3 decimal places for everything except money in applications. Natural log of 22. This is straight calculator work. And round to 3 decimal places. Right? Again, stop if we're going too quick, if you're not getting these. Now you're going to get some simplifies. I know we should be able to do these easier, but it still frustrates me, so I'm super meticulous with this. When we're asked to simplify an expression in exponential form with logs and so forth, let it equal z. We've done this before, and sometimes it's really effective. With logs, it's very effective to do this. So let this equal to z, and then use the definition of a log. Be very meticulous with the definition of a log. What does that mean for us? If we switch this into logarithmic form. Say it.
Log base e equals ln.
Log base e of what?
F9.
No. Of z equals,
ln.
what's ln? Is that girl on the TV that always has the dancers and singers on?
Yeah, equals ln.
Ln.
Wow.
Natural log.
Natural log of 9. What's a logical conclusion if we change log base e to natural log, if we don't want to write log base e? What's the natural conclusion here? C must be equal to 9. Therefore, e to the natural log of 9 simplifies to equals 9. E to the natural log of 9, we're pretending it's equal to z. We're pretending so we have an exponential equation. We can take the exponential equation, use the definition of a log, e becomes the base, the power is what the log is equal to, z is what you took the log of. Log base e is natural log. Natural log of z equals natural log of 9. Logical conclusion, z and 9 must be equal. We don't solve for z because we added z, we're pretending. E to the natural log of 9 simplifies to the 9. That's it.
Can we go over natural logs?
Natural log means log base e.
Okay.
We don't write log base e, we write natural log.
Okay.
Right? Nobody writes log base e. I know early on now, we're early, so it makes sense to do that, but this step you'll get tired of doing that really fast.
Shouldn't the natural logs be NL?
Again, this was, I think the research I showed came up in France,
Yeah.
and I think they were calling it the log natural.
Oh, okay.
And I'd have to go back and really look all that stuff up again, but that was my recollection.
Okay.
And I wasn't there, so I have no say in any of this.
Okay.
Right? The second one, again, if you let it equal to z, how would this look when you switch it to exponential form? What would this become in exponential form? 3 to the power of z equals 27 to the x. Robert, what's another way to write 27? 3 to the third. Why would I want to rewrite 27 as 3 to the third? To get the same base. Sarah, how does the right side simplify? The right side. Okay? Paige, how does the right side simplify? 3 to the 3x power equals 3 to the z power. Sarah, what's a logical conclusion to make here? This is my volume control. You may be saying the right thing, I just can't hear you. Okay, Ellie, what's a logical conclusion to make here? Okay?
Oh!
Sarah, I'm going to put a 4 in the circle. You can put anything you want in that rectangle, but it has to be a true statement. 4. Can you tell me something else I could put in there and make it a true statement? Is there something else I could put in this box besides a 4 where this would be true? You're second guessing yourself up and down the floor here. I want to put something in this rectangle, and I want this statement to be true. Let's try some different things. Let's try 5. Is that true? No. How about -8? No. What can I put in the box that's going to make this a true statement? Anything else? No. No way, no how. What has to be true about the circle and the rectangle? They have to be the same. What's a logical conclusion? Write an equation down here. What's a logical conclusion? We have this. What has to be true? Not helping at all. If this isn't this true, what has to be true here? want you to write an equation just like I'm doing right here. Look at this, Sarah. Take this over here. Do you see how these are correlating?
Yeah.
What is the circle in my equation right here? And what's in the rectangle? What did we decide had to be true about the circle and the rectangle? What has to be true about this equation right here? Who has to be equal? I don't have a 3z. The circle has to be equal to the rectangle. Doesn't z have to equal 3x? Are you not seeing that at all? Are you sure?
Yeah.
I need you to understand, we've done, this is review from chapter 5. Bases are the same. Powers are the same. If the powers are the same, bases have to be the same. That's from chapter 5. So I expect everybody here to be making the conclusion that z and 3x are equal. Does that seem logical?
Yeah.
But it's all about same base. As soon as these bases aren't the same, like here, where it's a 27 and 3, then we're toast. Okay? So why did we switch the 27 to 3 cubed so we would get same bases? Exponents have to be the same.
We have to have the dots for our answer.
Depends what you want to do. This is Algebra 2. I'm showing you how to do this correctly mathematically. Am I going to mark you down for not having the therefore? No. Okay? But I'm going to show you how to do it correctly. So our conclusion has to be that this simplifies to 3x. You can't give me an answer of z equals 3x because we are the one that put the z here. Okay? Any questions on that? This is, when we get to here, we're back to chapter 5. When we're here with the log, now we're stuck in chapter 7. We have to be able to get out of the log equation to something that we're more familiar with. Okay, so here's another one. 10 raised to the power of log of 6.7. We want to set that equal to z. And we want to change it to a logarithmic equation. What would that logarithmic equation look like? What would the log? We're doing the definition of a log. Use the definition of a log or an exponent form. What would it look like logarithmically? Stephen, what would you put? Here's what it looks like. This is called the definition of a log. Log base b of, what did they give you? In your notes, I have a y here. Y is equal to x, then b to the x is equal to y. We have the right-hand side. What's in the b spot? What's in the x spot? And what's in the y spot? Now I want you to take those blocks and put them in these holes right here. So I want to say log base 10 of, nope, it's the y spot, that's z, equals log of 6.7. That's the power spot. Remember, a log is an exponent. That's the exponent. This is the base. There's the b. Right here. Equals. Goes into that spot. You have to be able to manipulate this back and forth, back and forth, back and forth. Log base b of y equals x.
log the log from the
This is what we do. This is how it works. This is all I'm talking about right here. We stop right here.
Oh, just
All I did was use the definition of a log. I haven't finished anything. Right? Can you go from this black statement, adding equals z, and turn it into the red statement? That's where we are. Melted. What's log base 10? No? Common log. So we have common log of z equals the common log of 6.7. What's the logical conclusion?
Z equals 6.7.
Z has to equal 6.7. How does 10 to the log of 6.7 simplify? 6.7.
We can't cross out.
You don't. You're just making a logical conclusion. And again, Penelope, this is all I had done to this point. I just want to make sure everybody can get to here. Then we finish the work. Do you understand what I'm saying? Sure? I don't think I'm communicating very well today. Yes, sir. Big, huge numbers and really, really small numbers. It's like a little bit like exponential, but better. So really huge numbers you end up dealing with logs. Examples would be things that work on logarithmic scales are earthquakes. So when you hear like a 5.7 earthquake, that's the power of 10 that you raise to. So when you look at a 5, earthquake of a 5, to an earthquake that's a 6, it's not from a 5 to a 6 bigger, it's 10 times bigger because it's a power. Musicians, I'm not a musician, but sound is done in decibels. That's a logarithmic scale also. So those are two simple examples of where you get applications of logs. Okay? Let's try this last one here. See if we can switch this. We'll make this a z. Can you switch that to exponential form? Can you switch this to exponential form? Again, those of you who are just sitting here warming a seat, you should be saying, hey, I love this class so much, I know I'm going to get to take it again. I don't need to do anything right now. Okay. Remember, we're trying to go with this idea right here. So we want to be able to take this definition of a log, and you're in log form right here. Okay, here's your base. This doesn't look like a base, but that 2's down here. This is what we're taking the log of, and I made it equal to z. We're looking at this side. So I want you to turn it from the base of this equals x. I want to switch to this form. So what's in the b position from this? 2 to the z, not 16. 16 to the power of x. Does that make sense? So when we make this loop, here it is. We're just making the loop. And we're going to say 2 to the power of c equals 16 to the power of x. At least, what's another way to write 16? 2 to the 4th. Carlton, how does 2 to the 4th to the x simplify? Much thinking. How does 2 to the 4th to the x simplify? 2 to the 4x. That's all we want to do. Just get rid of those parentheses. Well, I'd like to know what the next line is. Would be even better than the end. What would the next line say? Fantastic. That's a great logical conclusion. If the bases are the same, the powers are the same. This is not our answer. Who can tell me why this is not an acceptable answer?
Because we added.
We introduced C to this problem to make the definition work for us. So how do we have to say the answer simplifies to just the 4x? Okay, and I know that it's tempting to just stop going, hey, I found C, we're good. Not what we're looking for. Okay, so when we continue this tomorrow, we'll start with, we'll look at the graph, we'll look at the inverse. Homework 11 only tonight. Homework 11 only, page 503, 3 to 27, not odd, all.